Hi and welcome to another episode dedicated to the development of the PiPicoFX, an open source multi-effect device. In this video I'll cover the following topics. I'll talk about the development of two new effect programs, a Shimmer Reverb and a Tremolo effect. The first is an effect which I consider impressive at first sight but also funny to use. The second one, the Tremolo, is sort of a low-hanging fruit from a development perspective. But I added a personal twist to it which makes it stand out at least a little bit. The video ends with a few words about three technical topics: clocking the Raspberry Pi Pico to 200 MHz, along with some memory layout-based performance improvement. The second technical topic is related to how I got rid of I2C noise by software means. The first technical topic is related to the daisy seed version of the PiPicoFX. In order to be firmware upgradable by an end user, I had to implement a mechanism for upgrading the firmware, which is not too complicated to use, but also not too complicated to develop. I'll start with a bit of theory explaining the working principle of a Shimmer Reverb as implemented in the PiPicoFX. The basic ingredients of a Shimmer Reverb is reverb, of course, and shimmer. For the latter, I harvested unicorn firm at full moon nights. No, jokes aside. Shimmer is a pitch shift plugged into a feedback loop of a delay. The reverb is a pretty standard algorithmic reverb topology consisting of three delays, comp filters, whose signals are summed up and pass through two all-pass filters connected in series. This wet reverb signal is then fed into a delay, which has a delay time which is short enough to be slightly audible as echo, but long enough for a gradual shimmer build-up. As usual, the program can be influenced with parameters, at maximum 8. I decided to boil the parameters down to 3 since we have 3 potentiometers which can then directly be assigned to each of the parameters. The first parameter, P1, controls the characteristics of the shimmer effect, or more detailed, the shift down-up amount of the pitch shifter in the delay. The second parameter, P2, controls the length of the reverb tail and delay. Technically, the parameter is a bit crude, but a good starting point for further tweaking. The third parameter, P3, is a mix controller allowing to blend the unprocessed with the processed sound. Now I want to give an insight on how I implemented delay-based pitch shifting, since it has some interesting properties from a music theory point of view. The basic principle is rather simple. Record audio and play it back at different speeds. Faster for pitch shifting up effects and slower for a shift down effect. In the digital domain, this is achieved by placing input samples into a short circular buffer and reading the samples back at the pointer which moves relative to the right pointer. If it doesn't move relative to the right pointer, we end up with a constant delay as indicated here. The red dot stands for or visualizes the record pointer and the record pointer, and the green dot visualizes the playback pointer. When the read buffer increases faster than the write pointer, we have a shift up effect. The real difficulty lies in the real-time requirement of the effect. Therefore, the buffer size should be as small as possible to introduce the least average delay. However, comp filtering should be minimal as well. Also, when the read pointer surpasses the write pointer, as it was the case now, we have a discontinue of the read buffer since we switch from the newest to the oldest sample or vice versa. Untreated, this would result in glitches and crackling. The approach to prevent this is to gradually crossfade the read pointer with a second one when it approaches the write pointer. This greatly reduces clicks but also adds unintentional frequency filtering. In the literature, there are many more sophisticated approaches, but they surpass my limited abilities as a software developer. Now let's talk briefly about an implementation detail which defines some musical properties of the pitch shifter. I decided that at each sampling event, the pitch shifter pointer is only incremented by a quarter. Therefore, if the write pointer advances by 1, the read pointer at minimum advances by a quarter. So we have the following shift down and up ratios. If the read pointer advances by 1, we have a ratio of 4:1, which results in an effect signal being 2 octaves below. If the ratio is 2:1, 1 octave below. If it's 4:3, that means if the read pointer advances by 3, while the write pointer advances by 4 quarters, so to say, we have we have an effect signal of being exact a fourth below. If the ratio is 1 to 1, obviously we have no shift. The effect then is just a reverb fed into a delay. And if the ratio is 4 to 5, a third above, 2 to 3 is an exact harmonic fifth above. The ratio 4 to 7 is rather interesting because this sounded a bit odd when I tested it. This is actually a harmonic seventh above, and this is still a harmonic ratio which is used in just intonation, but it's rather unusual for listeners which are used to the chromatic or the equal tempered scale. If the ratio is 1 to 2, then the signal obviously is an octave below. Of course, the increments could be larger than 8, but for a pitch shifter and also this shimmer reverb effect, this is rarely useful. Now for some sound demos. Last demo, Zelda effect using guitar. Raw sound. Tremolo. This effect is basically an amplitude modulation with a periodic signal, typically a sine wave. This effect is or was a standard in many tube guitar amplifiers. What makes the implementation special is the definition of the modulating function. The sine shape, this is a visualization of one period of the modulation function. The sine shape can be blended with a square wave, allowing a gradual change from smooth to more chopped tremolo sound. Here would be chopped, and here more smooth, and this can be blended. Also, the pulse width can be modulated independent of the blending. So this is how the modulation curve looks, and now also for some sound demos. mostly on. Symmetric. Mostly off. Now for the first technical topic, upclocking. Since officially supported by the Raspberry Pi Pico SDK, I decided to also increase the clock rate from 120 MHz to 200 MHz. Since in this configuration the flash access is slower compared to the RAM, I also moved time-critical routines from flash to RAM. As seen here, the performance increase is considerable. This of course allows for much more or much complex effects. Then the second technical topic is how to treat I2C noise. When building the first stomp version of the PiPicoFX, I noticed some noise issues, especially in the high-set input. This was due to the I2C communication between the main MCU and the stomp switch expansion MCU. I mitigated this by using shielded cable, but it never went away completely, sadly so. So I decided to replace pulling the extension IC with a multi-master I2C configuration. This has proven to be at the very limit of my embedded software engineering abilities. But in the end, the noise was reduced to almost nothing. Since the I2C line is now only busy when the stomp switches are handled or the LED color changes. Also the bandwidth on the I2C bus of course is greatly reduced as well, which again opens the door for further improvements and extensions. Third technical topic, firmware upgrade. When thinking about the mechanism to simply upload a firmware, basically two options exist. Over the air, aka using Wi-Fi. Since I used a full metal enclosure, this option already makes little sense from a physical point of view. Besides this, it would mean to add a Wi-Fi or Bluetooth capable MCU, which seemed too complex both from a hardware and software side. The second option is USB. This is complex as well, but at least physically doable. The STM32, similar to the Raspberry Pi Pico, provides an out-of-the-box USB DFU interface, allowing the reprogramming of the internal flash. The problem is that most of the PiPicoFX firmware resides in an external QSP interfaced memory. So I had to think about how to program this as well. The approach I used so far was UART. Of course, I had to write an upload tool and the QSP write interface on the hardware side. Also, the UART interface is pretty slow, which becomes annoying also during development when firmware upload cycles are short. I then decided to swallow the bitter pill and implement a DFU, which stands for Device Firmware Update or Upgrade interface, which writes both the flash and QSP memory in one go. This works well in conjunction with the Linux command line utility called dfo-util. What I plan to do is to implement a web DFU based solution which I'll put onto my website. When plugging the daisy seed based PiPicoFX into a host, this can be a PC, Mac, tablet, phone or any other USB host capable and device with internet access, it will present itself as an USB device which contains a HTML file with a link to the firmware update subsite of my homepage. From there, firmware update can be done via web USB. Of course, this approach was a bit copied from Electrosmiths, the company behind the daisy seed. They also provide web USB options to upload the firmware, but only implementing the standard STM32 interface. If you're still there, congratulations. Please share if you find this content interesting and subscribe if you want to stay updated. Until next time.